Okay, so one student didn't have a class, stuck around. And they only had some place out to go, he stuck around for a while. But anyhow, one student worked this thing out for their rectangle. You got it handy? That's okay. Yeah, it looks something like this. It's smaller, so there's more wiggle room. So we might refer to it. So right here's all the calculations for the G function. Now, it's labeled F. Okay, because it really is the same function, but it's not generally the same function. Okay. So I want to go ahead and make sure we understand that these are G's. Now you can't read them, you just got to know that they're G's. You can see that little loop down below, which indicates it's a G. Maybe it looks like some fancy interval. I don't know what it is. So there we have it. Okay. Now all the calculations are there. You have 7.5 centimeters of the sample point here. That's the value of G. That's how far this thing is out of the plane at this point. It's a large version of that rectangle. And down here it's less. It's 6.7 centimeters. 7.5 here, 6.7 here. We can see that this student has labeled the two X. Well, here's the line where X is constant. Here's the line where Y is constant. So this is basically your sample point where these two lines cross. And everything is calculated based on the sample point. Now I'm going to observe that the slope here differs from the slope here, differs from the slope here. Okay, this is pretty level. This has got some slope. This has got some slope. Okay, so the slopes are all small, and they probably have a factor of 2, or even maybe 3 difference between one point and the next. So that's going to be important. But and the function values, vary from here to here and from here to here, obviously. Okay. Also, you have a dip here. Okay. There's all kinds of irregularities in this. In any case, the measurements based on the sample point were that the value over here is close to 7.5 centimeters. You're going to multiply that by this distance, which was said to be 2 centimeters. Okay. So 7.5 centimeters multiplied by the 2 centimeters gives you 15 centimeters squared. That's your approximation to the line integral from here to here. Now, if you knew the equation for the function and could integrate it, you could do that line integral. But that's the approximation. The approximation over here is based on the 6.7 centimeter value of the function. Again, the sample point over here. Okay. Now let me clarify something I said previously. I said you have a line here and a line here. So here are your sample points for the line intervals, right? For the C2 and C4. And the sample points for the C1 and C3 are here and here. We're essentially basing our slopes on these two sample points for the Fx and on these two sample points for the Gy. Right. Gy is measured. Sorry. Fy is measured from here to here. GY is based on your measurements. GX is based on your measurements from here to here. But it's Y that's changing here. And the function here is F. Function here and here. So this is your F function. And your G function is over here. And again, we slope is based on these two sample points. You could say, well, we're sort of using this as a sample point. So we rest the little strap here in this direction to estimate out Y, and here to estimate GX. Okay, but really what we're doing is from this point to this point, from this point to this point. You kind of think about what I mean. I didn't say it real clearly. There it is. Okay. So again, we get our approximations in line intervals. Very straightforward. We just assume that G is always equal to 7.5 from here to here. And that's going to be pretty close. That doesn't vary by much. And always equal to 6.7 from here to here. Then we assume that the slope everywhere in the X direction is, where is it? Okay. GX, right? Partial G with respect to X, which is this. We already determined that the Fy was this, and you know what I did? I used the Fy from my rectangle rather than from your rectangle, right? I didn't have the right Fy. So let's just pause for a second and see if we get the right Fy and see what happens there. Okay. And what we got here is still plausible, but probably going to be a little more accurate, hopefully, if we use the right measurements. Okay, in discussing this after class, I wasn't thinking, and I used the negative 0.14 slope that we got for Fy. Okay. And that wasn't correct because that was with a completely different function. And that was with the big block, not the little block. The Fy is going to be the difference between here and here, which is 0.02 centimeters, right? Divided by this distance, which is 2 centimeters. So that's just 0.01. Okay. So we can say that well, that's our Fy. Our negative Fy will then be negative 0.01. And we multiply that by the delta Y times delta X. I had to do that down here to get around this thing, which I wisely wrote here, but that's, we're going to follow that. The arrow tells us where we go. So this should actually be 0.16 times 2 centimeters. Yeah. Which is then 0.32 centimeters. One six times 3.2, not 0.2. It's not even that. 2 times 4.7 is 9.4. 9 times 0.16 is 1.44. Okay. And it's a little more than 9. So I'm going to say it's about 1.5. Check my arithmetic. But now, compare this to the sum of the two line intervals. Okay, this integral of C2 plus integral over C4, right? This should equal okay, we don't have the whole thing. Okay. According to your calculations, the integral of f dx plus g dy is what? Now your integral of f dx was 1.6. I'm sorry, the g dy was 1.6 centimeters squared. And the integral of f dx was difference between this and this is only 0.02 centimeters. So that the integral here is only going to be 0.02 centimeters times your distance here, which was 4.7 centimeters, right? 0.02 times 4.7 is like 0.1. Okay. It's really easier to do this with symbols, but doing it with numbers makes the symbols plausible. Okay. So this is your total integral, which ought to equal the integral of negative fy plus gx. Well, this is 1.7 centimeters squared. And actually, this is -1 because we're integrating in the negative direction, -0.1 centimeters squared, and coincidentally, about 1.5 centimeters squared. Okay. Now that should get your attention enough that you again look at Green's theorem. Okay, and the proof, and why Green's theorem says what it says. Because this is actually astoundingly accurate. Okay. And then I kind of need to work it out for my own rectangle. And it's going to be a little less accurate, I think, because you got more variation than bigger rectangles. But there it is. Okay. And you understand now, as you shrink your intervals down on every rectangle, you're going to approach a plane at the top of the solid. Okay. In other words, a function above any small rectangle down here doesn't have time to change its slope in any direction very much. So it's pretty much a plane. And you can also easily prove that if you've got a plane, then this always has to come out exact. So your figure didn't have wasn't much of a plane, but it still appears to have worked out. I mean, here it is again. Look at it here, and you got all kinds of waviness here. If these numbers are accurate, if we did these calculations correctly, it's fairly coincidental that it came out exactly the same. If I cut this thing in a plane, and the measurements were all done accurately, it would have come out exactly the same.